For the sound coming from your speaker right now to reach your ear, energy is needed. Today we'll be explaining its link with power, as well as how the propagation of this energy changes our perception of its magnitude, with the concept of intensity.
Imagine a speaker producing a noise and a microphone interpreting that noise. The noise production requires power. Power is measured from the emitter, while intensity is measured from the receiver. Or to put it even more simply, power is often described as the cause, while intensity is the effect. The relationship between these two concepts is much more complex than its simple cause and effect. But before explaining these subsidies, let's start by understanding what is power.
Sound power in watts is equal to the acoustic energy or sound energy in joules divided by time in seconds. Measuring sound power is equivalent to measuring a quantity of energy released in a given period of time. Specifically, this is acoustic energy, which is proportional to the pressure amplitude squared. This pressure amplitude is the measure of how much air is compressed when producing a sound wave, as you can see here.
If I transfer just a bit of kinetic energy to the guitar string, the variations in air pressure it will produce will not be very significant, so the sound energy and therefore sound power is low. Now if I transfer a lot more kinetic energy, the string will traverse a longer vertical distance in each oscillation, meaning more air particles are compressed for each sound wave. Finally, if I give, let's say, 1 out of 10 of my maximal plucking energy, but I do it 10 times over a period of a couple seconds, the sound power will be less significant than if I give 10 out of 10 of my maximal plucking energy once over a very short period of time. So to recap, sound power is the amount of sound energy produced in a given time.
Sound wave intensity builds off this concept since it is proportional to sound power. Sound intensity is sound power divided by an area which measures it. Intensity is watts per meter square, is equal to power in watts divided by area in meters squared. This area can be represented by 4 pi r2, the formula for the area of a sphere.
Let's say this Sharpie ink represents concentrated sound power. The uninflated balloon covered in Sharpie represents the initial moment the sound is produced. Let's say I put 1 gram of Sharpie ink to represent 1 watt of power. As I blow the balloon, the amount of Sharpie ink stays the same because sound power, once it's been produced from a single sound, will not change. However, you can see the darkness and therefore the concentration of the Sharpie ink gets less and less intense because as the balloon expands, the amount of Sharpie ink at any given point is smaller. The pigment intensity changed, and the same is true for sound.
Let's say when I was putting Sharpie ink on the balloon, it's like charging my laptop with electricity. The moment I start blowing the balloon, it's like I click the play button on my favorite song. If I put a tiny person walking along the surface of the balloon at this moment, he is basically bathing in some deep, concentrated Sharpie ink. But for a person floating in the air a couple centimeters away, when the balloon reaches him, it's more like a Sharpie ink puddle he found himself in. In both cases, the intensity of the sound was different at a specific point, because the area through which the sound spread became bigger. As you could tell, the person floating in the air was at a further distance from the original sound source, therefore sound intensity depends on the distance separating a listener from a sound source.
This follows the inverse square law. Sound intensity is proportional to 1 over the distance separating a listener from the sound source, squared. We can interpret this law with different shells of a sphere appearing as a sound wave advancing through a medium. In shell 1, let's say we have a 1 meter squared square, which represents 100% of what I'll call area A, which in turn always occupies the same percentage of an area for each shell. Once shell 2 is reached, this square only represents 1/4 of area A, and once shell 3 is reached, the 1 by 1 meter square only represents 1 over 9 of the area A. Since the power stays the same, it must spread over area A, so the intensity in the 1 by 1 meter square is much smaller than what it used to be.
To better understand sound density, we should also explore the formula intensity equals pressure amplitude squared divided by the density of the medium in kilograms per meter cubed and the speed of the sound in meters per second. Since the speed of sound is dependent on temperature, we can see how being in a colder medium can have an effect. However, it's also important to take note of a phenomenon known as temperature inversion. Finally, other environmental factors affect sound intensity, especially depending on where the listener and sound sources are located. Indoors especially, reverberation increases sound intensity due to echo, meaning sound intensity at a specific point is actually higher than sound power divided by area. This reverberation depends on the shape and materials of the room, which influence the amount of sound waves which can reach the listener. This is partly why sound intensity is lower outdoors, as long as temperature and windiness are the same as indoors. In an open space with no obstacles, only the direct sound wave will reach the listener, while in a closed space, each time the sound wave bounces off a reflective surface, like a floor made of ceramic tiles, let's say, that sound wave will also reach the listener, though it takes a bit more time to do so, creating the echo effect.